So last but of course not least, I'm happy to announce Mateo de Bardeci with deep learning applied to electroencephalogram data in mental disorders. Mateo.
Okay, hello. I'm very happy to be here presenting our findings of our systematic review that we did with Sebastian and with Chang. So, well, very quickly about the methods. It's very standard. We looked for some words that includes deep learning, LSTM, and psychiatric disorders. And we end up with 30 studies. And we extracted the information about the clinical domain, the EEG data domain, and the deep learning domain. And what I want to talk about here is about the deep learning domain, and in particular, the testing method. And yes, so very quickly, the difference between statistical learning, statistical testing, and machine learning is the most important difference is that the statistical testing is based on logic. So you start with an hypothesis, you make assumptions, you compare it to the observation, and then you can calculate a p-value or a confidence interval. And usually I don't say this, but the reality is that even if you make mistakes in the assumptions, if the assumptions done are like 100% compatible, usually you can estimate the impact of those mistakes, and the paper actually have some scientific value even when doing mistakes there. Also because the p-value is not the only thing that you calculate, you also calculate the effect size. So usually I don't say this, but the reality is that yes, there is scientific value even when this is not the case. But with machine learning, since everything is based on performance, and you can only evaluate the performance with a test. So everything is based on testing, and mistakes in testing can imply that the scientific value of your project is really zero. So this is why I'm focusing here. And yes. So while we were analyzing the papers, we found out that, and we were pretty surprised that the accuracy are very high. And just for the context, what they were trying to do is to classify diagnosed patients, schizophrenia or depression with healthy controls. And this was the main task that the people did. And we were pretty surprised that they could classify depression with 99% accuracy and 96% accuracy. And I don't have to tell this audience that it's not necessarily so that it doesn't make so much sense to be able to do that predictively well. So the question is, what is happening here and what are the main problems? So it also correlates with the independency of the test data, and this is one of the things that I want to talk about. So what are the main testing techniques? The most common one when you have enough data is to just separate one chunk of the data. Usually it's between 25 and 50%. Here is 50% in my slide. Usually I do like 30%, but yes. The problem is then if you don't have enough data to make the split, then one thing that you can do is cross-validation, that you train on the data set, but you leave maybe one patient out or maybe two, and then you test on that patient that you left out, and you iterate through the whole data set and until you tested everybody and you trained on everybody. The important part here is that you can not test too many models, because then you are making multiple testing, or and it's actually the same as overfitting the testing data. So this is the first thing, that if you test it, then you cannot come back and test many models more. And the same is true for the cross-validation. So then I'm going to explain what are the possibilities to choose the model that you want to test without overfitting the test data. So yes, what we found out is that people were testing too many models. They overfit the test data. The other thing that we also found out, and it's very important, that the train and the test data are independent. You cannot have the same patient on one side and the other side. So those must be independent. And yes, that's almost the only mathematical thing that needs to be done. And yes, then we are also going to see why this happened. And also some papers only reported accuracy, and sometimes if you have a balanced data set, accuracy is not the best metric to evaluate. Yes. So the possible solutions is, in the case if you are doing something like this with the splitting, is to add a validation set. So actually you take the training set, and since you can do what you want with the training set, then you can add a validation set in the training set, and then you choose your model using the validation set. So you are like, it's like you are simulating testing the model in the testing set, but with a step before with the validation set. Yeah, so I think this part is more or less clear, I hope. But the other way, if you don't have enough data to do this, you can do nested cross-validation. And nested cross-validation is actually the same principle, but with the inner cross-validation in the same way. This is like an inner testing set. You do an inner cross validation. And let's say you want to try out, I don't know, 10 different models. Then you optimize those models in the inner cross validation, and then you choose the best model in the inner cross validation, and then you test it in the outside. And you do that with every fold also, so with iteratively. So this is one way to not overfit the testing data. So what happened with the independency? The problem was that many people did something like this. They took the EEG, they segmented it, and they had then, you know, something, a lot of data points for one patient. And what they did was they segmented the data, and then they split it. And that means that what happened probably is that you have the same patient, some segment of the same patient in the training data and some in the testing data. So actually, the machine learning model was learning to identify the EEG, the same EEG, but in the testing data. And yes, that's why they had like 99% accuracy, because they were just trying to identify the, yeah. So this is very important. And it's a shame because actually some of these models and the pre-processing were interesting, but because they did this mistake, the whole paper and the whole project has no scientific value, because there's it doesn't make so much sense. But yeah, so the main takeaways is the first thing is to decide how to test the model. Because everything is based on a testing and on a performance. And even if you are going to interpret the model later on, the interpretation and these techniques on finding out what the model is optimizing on, the performance must be there. And then deciding how to evaluate and how to test the model is the best, is the most important part. Then think about model selection. So if you want to try different models, and with different models, I'm also saying if you change some parameter of the model, some hyperparameter, like I don't know, if it's even the same model but with some changes, it also falls into this category. Think about model selection, and if you want to do validation sets, nested cross validation, whatever. Make sure that the test data is independent. Because if it's not independent, everything that you do has no scientific value, because the only thing that you have is the testing. And then everything else. So we actually also, in our paper, we have also more things that might be important or that you are interested in. But the three things that are key are the first three here on the left side. And then these are also some opinions of and experiences that we have. But yeah. So, do you have any questions?
So thank you, Mateo. I think it's very good that we have data scientists talking here at the IPEG meetings. It's so important because no one of us can overview all the methods and things we can do. Other questions from the audience? Yeah, I saw it. Okay, so one of the recurring discussions we are having in my group is related to how a final model is determined. The one that can be used on completely new data sets. Regardless of the CV strategy, how would you recommend choosing building a final model? Maybe based on the best performing outer model, or refitting on the whole data set using the best hyperparameters?
Yes, okay. Two parts of this question. So I'm pretty happy that this question came up, because I also wanted to talk more about this. So you always have to decide which metric you want to use to evaluate the model. So for example, if you are thinking about accuracy, it's, for example, in this case, if you would just classify everything as a normal transaction, then you would have 99% accuracy. And accuracy might maybe not be the best metric to look at, and the metric will depend a lot of the question that you are asking and you're trying to answer. And yes, now about the CV strategy, how to, yes, the best model is actually something that is subjective, and it depends on the question that you are trying to answer. Maybe some model might have more sensibility, some other model that maybe has more specificity, and depending on what is important, that's what the best model is about. And now about the cross-validation. So the thing with the cross-validation is that you are assuming that your model, you are redefining the model in such a way that the ensemble of models is your new model. Was that clear? So now everything here is one model, even if you are taking many models together. This is like the mathematical way of defining it. And the prediction then is going to be similar to the cross-validation if you then train everything again on the complete data set. So what I suggest in this case is to, yes, what you are doing in the inner cross-validation, use that for the complete data set. Just take the complete function of inner cross-validation and optimizing everything, and just that's going to be a function, and just put in the whole data set and make cross-validation again on the whole data set. Does that answer the question of, I don't know who this person was?
Yeah, okay.
Yes, sure, thanks. Okay,
Yes, sure,
perfect.
thanks. So thank you for that. Any more questions? Marcel.
Maybe you said it and I missed it. So what is the minimal number of subjects you need for machine learning?
Okay, I mean, there is no mathematical statement about this.
Okay, so 3 are enough?
No, I mean, there is an interesting paper of people who try to classify images, and they showed that actually with, like, do you know this ImageNet competition where you try to classify a lot of images, and they showed that with 10 images they had like an accuracy very high, like of 80%. And what they did was they manipulated the images in a augmentation. They did augmentation with the images, and they produced a lot of new images from those 10. So actually, that paper is really interesting because it shows you that it's actually possible to have a small data set and then augmented it, and then have good results. So yes, there's no mathematical limitation, and then there's no limitation.
Okay.
Yeah.
So let's add some jitter to the EEG data and then have separate data sets. Mateo, thank you for presenting.
Wait, Marcel
wants to extend the meeting.
Everything which has advantages has to have disadvantages. So regarding machine learning, what is your general opinion or your experience regarding the disadvantages?
Yes. So
if there is a short answer.
Yeah. So we have to think always that this is a tool. This is a tool for an end. So yes, it has disadvantages. Like every tool is for something in particular, and you have to, for example, if you have a hammer, of course a hammer is good for some things and bad for some others. And it being a tool. Yes, the disadvantages are usually the interpretability of the model, that it's not always easy to interpret. And there's a big field now of people trying to develop interpretable machine learning models and deep learning models also. And this is very important because obviously if you talk to a clinical doctor, they want to know what is happening. And I think that makes a lot of sense because they are also taking on the decision on what to do with the patients. So yes, the interpretability, and that is usually the main disadvantages.
So again, thank you very much, Mateo, for presenting here at the IPEG meeting.
Yeah.